Hi, grade 12s. Today we kick off the exponents and logarithms unit by looking at exponential functions, equations, their properties, and all that good stuff. One of the worldwide phenomenons that's very closely linked to exponential functions is the coronavirus. We can definitely talk about that, but for now, let's learn the theory behind everything and give us a foundation from which to build. So, let's take a look at the following three exponential functions and their graphs and see if we can detect a relationship between them. So if we take a look at 2 to the exponent x, it's represented by this nice blue curve that goes like this. If we take a look at 3 to the exponent x, it's represented by this red curve. And if we take a look at 1/2 to the exponent x, it's this curve here that actually is going to grow in the opposite direction. Now, to kind of see how these are similar, but also how they're different from one another, we're going to look at the properties below in order to guide us. So, first of all, for any function of the form c to the exponent x, there are the following properties. Here they are. The y-intercept is 1, okay? The domain is all real numbers. Word problems or contextual situations would be different, but for the functions themselves, x can be anything. X is an element of all real numbers. The range is all positive values greater than 0, so they can't be 0. As much as those curves look like they are touching the x-axis, they are not. They're getting closer and closer and closer and closer and closer and closer to the x-axis, but they never actually touch at the x-axis. And that actually, I'm going to skip ahead a bit, that actually brings us to the final bullet. There's a horizontal asymptote at y equals 0, which means that those curves never touch the x-axis. Now, as far as why they look the way they do, if c is bigger than 1, then the graph approaches infinity as x approaches infinity, and the graph approaches 0 as x approaches negative infinity. So if c is bigger than 1, if the base is bigger than 1, then you get something that looks like this or this, where they are going up and to the right, okay? However, if c is between 0 and 1, then the graph goes towards 0 as x approaches infinity, or the graph goes towards infinity as x approaches negative infinity. And an example of that is this guy right here, which is modeled up here. Instead of going up and to the right, that graph goes up and to the left. Okay? All right. Now, here we see that if c is bigger than 1, which is these friends right here, we say the function is increasing and is an example of exponential growth. However, if c is between 0 and 1, which is of course this friend right here, then we say the function is decreasing and has exponential decay. Some of these properties are going to change if there's transformations, and we will look at transformations later in this unit. We did a whole unit on transformations, so it shouldn't be a huge deal, but just giving you a heads up. Okay? Now, the next example says to complete a table of values for y equals 3 to the exponent of x. So, here is x, here's y. Let's go -2, -1, 0, 1, 2, and 3. And we're going to plug those in and see what we get. So through anything to the exponent 0 is 1. 3 to the exponent 1, 3. 3 squared, 9. 3 cubed, 27. So we can see the pattern here. Like every time you go down in the table, you are multiplying the y values by 3. Now, the reverse is true if you go up. Like if you go up instead of down, then you are dividing by 3. And that will help us fill in the last two spots above. When x is -1, y is going to be 1 over 3. When x is -2, y is going to be 1 over 9. Okay? Now that we have those values, we can go ahead and make our graph. And as you might imagine, it's going to be kind of hard to draw a ninth or even a third. So we're going to have to use a little bit of creative license here as far as what we want this graph to look like. It really, as far as your scale goes, here's what I think I would do. Obviously, we'd put this as 0. I'd put 6, 12, 18, 24, and 30. And for our x's, I'd go 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. And then try and plot what we can. 0, 1, it's going to be that point right there. 1, 3 would be right here. 2, 9, right there. 3 and 27 would be up here. And then working backwards, -1 and a third. Good luck. It'd be like this. So what we're going to do is we're going to try and draw a nice smooth curve that's going to kind of try and go through those points as best as possible. And that's kind of what I got there. So, and there it is right there. There's your curve. There's your function. And we can see that a function like this grows very quickly. So it kind of starts off small, but then the growth just takes off. And now that we've graphed it, we can go ahead and take a look at part C, which asks us to identify the domain and range. So the domain, as we said earlier, -infinity to infinity. The range also is going to be 0 to infinity. 0 is not included, so we use a round bracket. What about the intercepts? Well, there's no x-intercepts, but there is a y-intercept. So there's a y-intercept at 0, 1. X-intercepts, none. Make sure to specify that. Whether the function is increasing or decreasing, well, the function is increasing. And what's the horizontal asymptote? Horizontal asymptote is at y equals 0, otherwise known as the x-axis. And that takes care of that example. And we'll move on to the next question. So in this question here, we see complete a table of values for 1/2 to the exponent of x, and then graph the function. So we're going to go ahead here. I'm going to say we go like -3, -2, -1, 0, maybe 1 and 2. And the reasoning why we're doing this is because our base or our C value is a number between 0 and 1. So now anything to the exponent 0 is 1. If you have half to the exponent 1, you can get a half. If you square a half, you get a quarter, and that'll be here. So basically, if we take a look at the pattern here, we're dividing by 2 to get to each progressive y value as we go down. So if we're going to go the reverse way, instead of dividing by 2, we'd be multiplying by 2. And that's going to help us fill in the table number values above. So that's going to be a 2, a 4, and an 8. So y is going to be fairly straightforward. Then I think we can kind of do this, I guess. 2, 4, 6, 8, 10. For x, we can go 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, minus 5. And then we can go ahead and plot those points and graph it. So negative 3 and 8 would be up here. Negative 2 and 4 would be here. Negative 1 and 2 would be here. 0 and 1 would be here. 1.5 would be here. 2.25 would be here. And then we just try and draw a nice smooth curve through those points. So this time, we'll start here. There we go. We get something that looks like that. Make sure to include those arrowheads because the graph does keep going to the left and to the right. And that is reflected by the next step where we're going to go ahead and identify the domain, the range, and so on. So the domain is negative infinity to infinity. The range, 0 to infinity, round brackets on both because 0 is not included. The intercepts, there are no x-intercepts, but for the y-intercepts, there's just 1 and it's at 1. Now, state whether the function is increasing or decreasing. Well, it's going down from left to right, so therefore it's decreasing. And then what's the horizontal asymptote? The horizontal asymptote, HA, or HA for short, is the x-axis, so that's y equals 0. So there's a lot of similarities here. Even though we have a different function, different looking function, that's the same, that's the same, that's the same, that's the same, and actually that's the same. The only thing that changes is whether it's increasing or decreasing, and of course the actual look of the graph is different as well. Okay? All right, and we'll move on to the next one. Which exponential equation matches the graph below? So here we go. Well, how are we going to be able to figure this out? Well, here's the thing. So we can do this a few different ways, actually. We're not really confined to any real way here. Here's the thing. That's 0, 1. Okay? So if that's 0, 1, now to figure out a different value here, let's look at this right here. Negative 1.25. So, like, if we have 0, 1 right here, what do we do with 1 to bring it to a quarter? Well, we divide it by 4. So that should kind of make your spidey senses tingle a little bit. And it's going to be y equals something to the x. If we're dividing by 4 to get to a successive value, then that tells us that this is going to be a 4. So it's going to be y equals 4 to the exponent of x, just like that. And we know it's 4 and not 1/4 because the graph is increasing left to right. If the graph was decreasing left to right and we still saw a factor of 4, difference between two successive points, then we can go ahead and we could say it'd be y equals 1/4 to the exponent x. But in this case, it's increasing, so it's y equals 4 to the exponent x. Okay, so that's how we could figure that out. We really didn't even need, we didn't really even need the other point, 2 and 16. You could use it, and you could do this a slightly different way. But again, like, the whole point of this is basically just to go ahead and try and find a way that works. And if we look at the previous pages where we looked at those table of values, the nice thing with those table of values is we could see that when we go from successive one y value to the next one, we could see that you go ahead and you either multiply or you divide by whatever the c value is, right? So in this case, we really didn't even need that second point. And we'll go here to do our last example. So our last example here is the graph below shows the population of a certain type of bacteria under experimental conditions. So here we go. How many bacteria are present at the beginning? So what you kind of want to do here, I guess, is take a look at what the scale is. And every tick on the scale represents 2. So, and you can see it's halfway up. So how many bacteria are present at the beginning? It'll just be 1. Okay, it'll just be 1. And we'll use the pen here. It's 1. What's the domain and range of this function? Well, the domain, based on what this looks like, the domain is going to be 0 to infinity, like that. And the range is going to be 1 to infinity, like that. The left side of this graph starts right here. So that's the point that we have to use. The point is 0, 1, which is why the 0's here and the 1's here. Both time can go to infinity unless otherwise told, and also the number of bacteria can also grow that big also. Okay, so, and write an equation that models this graph. Okay, well, the thing is that what we can see here is that, let's look at successive points here, and here there's 1, here there's 2, then there's 4, and then there's 8, and then there's 16, and then there's 32. So some of you are probably already locking into this, but if you want to make a table just to kind of summarize it, you got 0, 1, 1, 2, 2, 4, 3, 8, 4, 16, and 5 and 32. So the $1 million question is, what do you do with one y value to get to the next one? And of course, you're going to multiply them by 2. So that's going to help us because it's going to tell us that it's going to be y equals 2 to the exponent x. Now, after how long will there be 5,000 bacteria? Now, later in this unit, we're going to find a magical way to answer this question directly. But right now, because that tool is not quite in our toolbox, we will have to kind of guess and check a little bit on this one. So we're just going to have to try and plug in numbers and see what we get. Okay, plug in numbers and see what we get. So let's try 2 to the exponent 10, understanding that 10 represents minutes. 2 to the exponent 10 is 1,024, so obviously it's more than 10. Now, exponential growth does get out of hand pretty quickly, so we want to pick a number bigger than 10, but not too much bigger than 10. So let's try 2 to the exponent 12. If you go 2 to the exponent 12, what do you end up with? Well, you end up with 4,096. Ooh, so we're getting closer, much, much closer. And so let's just go one more. So it's 2 to the 13. That's going to be 8,192. All those values are found on your calculator. So it's going to be between 12 and 13 minutes. And we have to really kind of wonder if this is a discrete or continuous graph. And if we think it's continuous, then we should go ahead and find where between 12 and 13 works. And so, we could see that 5,000 is a lot closer to 4,000 and 8,000, so that the exponent's going to be closer to 12 than 13. So why don't we try 2 to the 12.2, just to try and see if we could figure out what this is going to be. So if you go to your calculator and you go ahead and you go 2 to the exponent 12.2, we're close. We are at 4,705. That's not quite there. So let's go ahead and try 3. If you try 3, 12.3 rather, if you try 3, you are at 5,042. So we're a little bit too high. So it's going to be between 12.2 and 12.3, but closer to 12.3. So how about, and I'm going to carry this on over here, how about 2 to the 12.75? So, 275, not 75, 275. 2 to the 12.275 gets us closer, although actually not as close as we were with kind of around the same close as there. We're at 4,956. So that makes me think that we should probably go put an 8, 12 to the 2 to the 12.28, and that doesn't quite get us there. How about, okay, I'm just fiddling around on my calculator here, and the best I can do is 2 to the 12.288, and that gets us to 5,001, and that's good enough. So the answer to this question would be then that it's going to take 12.288 minutes. So it's going to take 12.288 minutes for the bacteria to reach 5,000. So there you have it. There's an introduction to exponential equations and their functions and some applications of them, as well as some properties. I'd like you to work on pages 342 to 345 in your book, questions 1 to 15.